We're going to continue talking about conformational analysis. Specifically, we're going to be approaching cyclohexanes this time around. And hopefully, if you've looked at any of the previous lectures, you can kind of build yourself a cyclohexane. And when you first draw cyclohexane, you'll notice it doesn't look very interesting, right? Well, it turns out that if you actually zoom in on the three-dimensional structure of this thing, you end up with something that looks more like this. And you'll notice there's all kinds of three-dimensionality to this thing. There's all kinds of bends and kinks in the chain here, or in the cyclic chain. And so what we're going to learn today is how to take some like really boring flat structured cyclohexane and turn it into what's called the chair structure. So we're just going to start right off here talking about the chair structure. And a lot of people can't quite see the chair. And so what I'm going to try to do in this very first video is to kind of draw what I see in terms of the chair. And there is the chair. It's really hard to see sometimes, but it kind of looks like there's the head of a chair, and then there's kind of where your feet would go. And so just to really make this a dorky video, I'll put a little person hanging out, drinking a drink. Well, it's a funky looking wine glass, but you get the idea. And the legs are down here. Drawn to scale. What an artist you are. And so anyway, this is the chair. And so what we're going to learn is kind of how to recognize the chair, how to do what's called chair inversions or chair-chair flips, which is something that is going to interconvert these two different groups. If I kind of put the chair on its legs, you'll notice it's a three-legged chair, right? And so you can see the three legs right there. 1, 2, 3. And it turns out that those are pretty important. Anytime you're looking at the legs of that chair, those things are called axial positions. And you'll notice that those axial positions, if you look at the kind of the area of the chair it comes from, it looks like the bottom of the chair is kind of pointed down, so the axial position is actually going down. So when I draw this in just a second, the legs of the chair, anywhere where I kind of see a bend that's pointed down, or like the end of the chair that's pointed down, I'm going to draw axial positions. And you'll notice that if you look at the accompanying group on every single one of those, right, obviously here in cyclohexane, these are all hydrogens. If you have a hydrogen that's axial down, there's also a hydrogen that's a position called equatorial, and it's actually going up if you look at it properly. And it actually turns out, as you look at this entire molecule, you'll notice that every single one of these has what's called an axial and also an equatorial position. We've got axial positions pointed down on the bottom of the chair. You'll notice that the other carbon has axial positions pointed up, right? And so the important thing to recognize is that every single one of these carbons has an axial group bonded, but, or in this case they're just hydrogens, I guess, but that they alternate, right? And so this guy is axial up, this guy is axial down, etc., etc. That guy's axial up, that guy's axial down, etc., etc. And that the equatorial groups, and by the way, by equator, just like the equator of the Earth kind of goes around the middle, those groups that are called equatorial kind of project outwards, right? This direction, if you can see my thumbs. And they also have a little bit of directionality that is the opposite of whatever that axial group is. So this guy, axial down, equatorial up. And then it switches. It's axial up, equatorial down. Axial down, equatorial up. So that's going to become important as we start to do chair-chair flips and such. So let's go to the next topic. So let's go to our chair again. And this time I'm going to show you the proper way of doing what's called a chair conformer of cyclohexane. And so the first thing that I always draw is the seat, right? So these bonds right here. And you'll notice that they're kind of, they're both parallel and they're kind of projected up a little bit. So let's see what that looks like in kind of an artist rendition. A very, very bad artist. All right, so there is the seat of my cyclohexane. This set of carbons right here, that's kind of where the head would go, is kind of pointed up. And so I'm going to do that as represented right there. And of course, on the other end, I'm going to take that thing and I'm going to project it down so that we can kind of see where the feet would go. And what we end up with is what's called chair cyclohexane. We're going to be drawing these quite a bit throughout the next couple of terms. And one of the most important things to do is to label your axial groups correctly. So let's go through and label the axial groups. And I truly do, the first time I was tasked with doing this, I would constantly look at model kits, and that's something that's really going to help you out. And so this guy, you'll see that the axial position is pointed up. And if you ever forget about that, remember that the cyclohexane almost makes kind of an arrow that tells you which direction your axial position should go. So here we've got this linkage that almost looks like an arrow telling us that our axial position needs to be up. And then the good news is once you've done that, every alternate group is also an axial pointing up. So let's put all those on there. All right, and so those are my axial H's right there. And also you'll notice that each of these kind of points up. Okay. So obviously, we've got to alternate our axial position. So now we're going to fill in all the axial down positions, or in the case of what we were doing before, those are the feet of the chair, right? So there are all of our axial positions labeled. Once you've got your axial positions labeled, that's where you can start to put in your equatorial groups. And notice the order with which I put the equatorial groups on. I start at the edges and then work my way to the inside. And there's a reason for that. So this guy is an axial down, so it must mean that the equatorial group is pointed a little bit up and then in the equatorial position. Same goes for this guy up over here. He's axial up, so I need to draw him equatorial down like that. So those are kind of the easiest equatorial hydrogens to start off with. And the next get a little bit harder to put in. So now, well, I guess this isn't that much harder, right? So over here on the edge, we've got an axial down. We're going to do an equatorial up. And then over here, we've got an axial up. So then we're going to do an equatorial down. By far, though, the hardest hydrogens to remember how to draw properly are the ones that are in kind of like the middle positions. So this guy right here, he's axial down, but what people often screw up is they're not sure which kind of, they know it goes up, but they're not sure which way to go. And so that's where we look back at our former beautiful drawing here. Notice that the chair is kind of sloping this way. Right? And so there's a slope, a downward slope to that chair. And what that's going to do for you is it's going to help you to remember these two hydrogens that are the hardest to remember. Notice that those hydrogens, they maintain the slope of that chair. If you do it the other way, it turns out it's wrong, and it's going to really mess you up when you get to talking about conformations. So what I'm going to do now is I'm going to go through and I'm going to label all the axial positions with red, and I'm going to show you what happens when I do what's called a chair-chair flip. Right? And so this is something that the cyclohexane is physically doing constantly at room temperature. It's constantly inverting, right? Going from one chair to the other, and watch what happens to those groups. Last drawing was getting a little bit crowded, so I redrew it, but this time I didn't include any of the hydrogens. What I'm going to do is I'm going to label in red all of those axial positions. And what I'm going to do is a chair-chair flip, or a chair inversion, as it's also called. So this is an equilibrium arrow right here. So what it's saying is that this chair form inverts itself to another chair form. And it turns out when you do a chair-chair flip, first of all, I'll do it with the model kit. So here's the chair I'm looking at now. When I do a chair-chair flip, I'm going to first pull this foot up and put it at the head of the next chair conformer. And the head, I'm going to invert until it's going down, right? And so if I do a little bit of reorganizing here, what you should see is a chair that's kind of projected the other way, right? And so this is the completed chair flip. What I like to do is I like to put my model kit down and make sure that those axial positions all provide a really nice chair. So that way I know I've done my chair flip correctly. And so now we're going to go through, and you'll notice that by inverting the chair, you'll notice that the slope of the seat has changed a little bit, and that's kind of one thing that helps me out a little bit when I have to redraw one of these things. So let's see if I can do it. Exaggerated a little bit, I guess. Not perfect, but you know, there's the result of a chair flip. Now look at what's happened to, first of all, let's concentrate on what used to be the foot of the chair, and then look at what happened with the head of the chair. Notice that group, that axial group that was down, is now going to also be projected down, but now it's in an equatorial position, because it turns out when you do a chair flip, you automatically flip your equatorials to axials. And this is something that will be super important for conformational analysis on cyclohexanes. So that little group that used to have the red dot, that is this hydrogen. And let's see if you can see it a little better. That is this hydrogen. And it turns out every single one of these axial groups, when you do a chair flip, they maintain their up or downness, but they switch from axial to equatorial. And then, of course, the contrapositive of that, I guess, is that each equatorial is now in an axial position. So let's fill all of that out. And we'll put little dots next to everything, but I think you can see what I'm talking about. Notice that I start by drawing all of my axial groups before I put in equatorials in general. Right, so there are all my axial groups, and I go to the outside, and I know that's axial down. This must be equatorial up. That's equatorial down. And I don't know why I started putting H's in, because it's just going to make it more crowded. But whatever. Okay, the edge of this chair, that's axial down, therefore this must be equatorial up. And then now the slope of the chair is in this direction, right? We switched our slope. So that tells us which direction to put these new hydrogens. There's a new hydrogen, and there's our new hydrogen. All right, and oops. Like I said, I don't know why I put all those hydrogens in there. So you'll notice that each one of those positions, right, I'll go through on the left side, and we can label the equatorial position here. You notice that that was axial up, now it's equatorial up. Then you go over another carbon. That corresponds to this, this position, right? That's an equatorial down. It used to be axial down. That right there, that what used to be the head of the chair, which was axial up, is now equatorial up, and vice versa. I'll go just around the thing here, you probably get it. Right? And so the point is that when we do a chair flip, all our equatorial positions become axial and vice versa. And that'll become important when we start to put in big, giant, bulky groups on things, when we start to talk about monosubstituted cyclohexanes, because it turns out that anything really, really bulky, right? So bulky means it has a whole bunch of carbons in it or something. So let's imagine like a CH3 group, right? Something that occupies a decent amount of space. It turns out that CH3 groups, or any bulky group, given its choice, would much prefer to be in an equatorial position, right? Because it turns out that if we put them, let's say that we just put a CH3 group on here, there's something called a 1,3 diaxial interaction. Let's put it here just because it's easier to label. Let's pretend we put a CH3 group here. it turns out that that CH3 group projected up in the air there has a 1,3 diaxial interaction, and usually you could abbreviate it with the sign for sterics, which looks like this, right? And so what you mean by 1,3 is that on carbon 1 here, there's a CH3 group that's interacting 1, 2, 3 carbons away with some other group, right? And so this is an example of what's called a 1,3 diaxial interaction. Turns out this particular carbon is also going to have a 1,3 diaxial interaction there with other axial group. It's kind of tough to see though, unless you've got a model kit. And so what I'll do here is I'll put some sort of bulky group on there. We'll start with CH3, I guess. And we'll see why that CH3 group is really going to prefer an equatorial position, which, by the way, we should probably put our CH3 group in over here. So that carbon corresponds to that carbon right there. So it much prefers this. So this is preferred. Now let's look at the model kit. So here's the model kit, and you'll notice now I've put in hydrogens. And the reason I did that is that you can actually hear the 1,3 diaxial interactions. Anytime you take a model and you can hear that thwacka thwacka, I don't know if you can hear that, but that's an example of some sort of steric strain that's introduced into a molecule. So that thwacka thwacka that we hear there, right, that's really what is the result of that, or what we call a 1,3 diaxial interaction, keeping in mind that this thing is constantly spinning. And so the electron density here really doesn't want to be anywhere near the electron density over there. And so what you can notice as we switch into this other form, right, we bring the head up and the head down to the foot. We make sure that our structure sits nicely on its 3 legs. What you can see here as I rotate around is that now this group is projected out this way, and these 2 hydrogens are much farther away, right? The thwacka thwacka is a lot harder. Of course, like with a Lego kit, I could really bend this thing over, but I can't really do that to a real carbon-carbon bond. So it turns out that bulky groups like this are much preferred in the equatorial position. And so if you look at your resource guides for Wednesday, you should be able to find kind of a guide that talks about how much equilibrium is favored towards an equilibrium, or towards the equatorial group relative to the axial group. And obviously, if I took this CH3 and I instead put some sort of really bulky tert-butyl group, and by the way, remember tert-butyl, that means that I'd have another bunch of CH3s out here. It turns out that tert-butyl groups have to be essentially in the equatorial position. They really, really would struggle in the axial position. So you've got, in a case like that, if this was some sort of really bulky group, you've got a much higher KEQ, right? A lot more presence of a whole bunch of product. And so one thing that we could do, which we're not going to like we did in the last lecture, is to kind of go through the energetic cost, though you certainly could do that. Another thing to kind of that's kind of interesting about this is, remember that Gauche interaction, right? That 60 degrees between different groups. Notice that if we sight down this bond right here, that you actually have a 60-degree dihedral angle between these 2 carbons. So these are actually Gauche interactions in here in a cyclohexane, right? And so if we had to go around and start to count those up, your head might start spinning. And so of course, like that whole idea of gauche, like if you have certain groups that end up being gauche to one another, that can be a damaging thing. Hi, Conrad.
What is this?
My son just stole my model kit.
Ew.
What'd you say?
Made a gun.
You didn't make a gun. It's a cyclohexane.
Oh. Are you on video right now?
I am.
Yeah, pew.
Pew pew. So the question is, where are we going with all this chair conformer junk? Well, it turns out that if we have a flat cyclohexane written somewhere, it turns out that just like we've talked about alkenes as being able to have cis and trans isomerism, it turns out this also exists in cyclohexanes. So here's a planar cyclohexane that I'm just going to label with, let's say, 2 CH3 groups. Keep in mind when you see the dashed wedge and the solid wedge, that has to do with the three-dimensionality on that particular carbon. So what I'm saying with this solid wedge CH3 is that it is poking out at us, and that there's a dashed wedge kind of behind it with a hydrogen attached. Similarly, over here, there's a CH3 group going behind the plane of this thing, and then an H that's kind of poking us in the eyeball there. But now we know that this thing is not actually held completely planar like this. By the way, this is Wonder Woman. She's making sure that I don't screw anything up. And so what we can do is that we can actually put this thing into some sort of chair structure. And in this particular case, we're going to notice that this thing is definitely going to prefer a very particular chair relative to the other one. So just at random, I am going to draw 2 chair conformers down here. One that is the flip version of the other, and then I'm going to show you how you can incorporate these 2 different groups. Okay, there are my chair conformers. And what I've done is I've color-coded both of these carbons so that I can show you how I'm going to incorporate them into these 2 scaffolds. By the way, I could literally, show that this blue carbon is any one of these. I just really like to kind of pick one carbon that's going to be right at either the head of the chair or the foot of the chair. So I'm going to just kind of put this blue one right here on this position. And one thing that I always like to do is I always like to imagine that my eye is above the plane, because it's so much harder to imagine my eye being behind the plane here. So my eye is above the plane, right? So I'm looking down at this thing. And so that position that I just picked, I know that there's an up position and a down position. And I know for a fact that I'm looking down on this thing, and it's poking up at me. So I come down to this blue carbon and say, okay, which of the 2 possibilities, is it axial that's going up or is it equatorial that's going up? And if I remember that, you'll notice that that arrow is kind of pointing me up. So it turns out that I'm going to start things off with a CH3 group, that CH3 group up, and kind of poking me in the eyeball here. And so maybe I'll put my eyeball in here. And so I'm looking down at this thing, and then if you'll notice, like this red carbon would actually be this one right here. I should say the red position is actually right here. And you'll notice that it's actually going down. So I look at this red carbon, I might as well label it. And I say, okay, what is the down position doing? Well, it's actually an axial down. So let's put that CH3 group right here. And it's going to look a little messy, so let's just put the CH3 group there. Sorry about that. So what you can see is I've actually put the bulkier group in both cases into the axial position. So as you probably would expect based on what I said before, is that whatever we do to do a chair flip is going to flip both of those things into an equatorial position and is going to be far greater preferred. So what I'll do is I'll keep track of the head of my chair there, and I know that the head of the chair becomes the bottom of the chair when I do a chair-chair flip. And so now my CH3 group, it's still going to be projected up, right? My eye is still up here. I haven't changed that. So that means that the up position now on this blue carbon is going to be looking like this, right? And so there's an upward projecting CH3. I can't put it down here because that would actually mean that I'm changing its relative orientation. And then the red one is right here, and so that used to be an axial down position. Now it's an equatorial down position, and I know that the equatorial down on that particular carbon is right there. So, and by the way, when you look back at this, you'll notice that we've got the up position correctly labeled and the down position correctly labeled. And let me put my colors in. So there's the head of the chair that became the foot of the chair, and then here's that other carbon. So we'll be getting a lot more practice at this. In fact, I'll probably do one more in this video lecture. This whole idea of being able to take a flat cyclohexane and turn it into a chair conformer and talk about which chair is preferred. By the way, I'll just label this one, this is preferred, due to those the minimum of 1-3 diaxial interactions. We'll see one more, and then in Friday's lecture, we'll start to throw a whole bunch of groups in there, and what we'll do is we'll actually take some chair forms and turn them into the flat forms. And there's different reasons that it's useful to be able to do these kinds of things. One thing I should mention is that it's not always true that one form is preferred over the other form. If, for instance, I had put both of these groups as both up, by the way, this thing is called, as you might expect, this is the trans isomer of dimethyl cyclohexane. If it was the cis, right, where both of them are projected up, you'll notice that that would have put a CH3 group in an equatorial position on one and in the axial position on the other. And then once you flip those, it would be still an axial and an equatorial. So in that particular case, there is no real preference between the different chair conformers. So let's try one more. I kind of like the idea of including a different disturbing minifig every time I start doing one of these. So here, we'll put Steve and his snake over in the corner here. Can't see Steve. Stay there, Steve. Okay, so let's start off with another one. Let's start off with a flat structure, cyclohexane, and I don't know, let's say an upward projecting tert-butyl group right here. And we'll make this the trans isomer, and we'll put a, oops, you guys can't see that, sorry. Watch out, Steve. Let's say we'll put a chlorine group right here with its electrons. Okay, so let's say that we wanted to turn this into some sort of a chair structure. So we'll make sure that Steve doesn't fall. Start off with the seat of our chair, the foot of our chair, the head of our chair. We know that we're going to have to do some sort of chair-chair flip. And there's our flip chair. And I'm going to just kind of arbitrarily assign that carbon to the foot of my chair this time. All right. And obviously, once I've done that, that kind of allows me to draw in everything else. So we know that our tert-butyl group is projected up and poking us in the eyeball. So here's my eye. So what is the upward position doing right here? Well, it turns out that is an equatorial up. And so let's just put T-but in there, which is typically a way that you can abbreviate that. And then you go around this thing and you go 1, 2, 3, 4. And then we get to the opposite side of the ring. 1, 2, 3, 4. So the chlorine group is coming off of that carbon, and we know it's projecting down. So what does that mean? Well, it means that there's an equatorial down with a chlorine group right there. We can do the chair-chair flip. That tert-butyl group still has to be projected up. The foot of the chair becomes the head of the chair. Now we've got our tert-butyl group pointed up. There's our chlorine that was pointed down. Now the head of that chair became the foot of this chair. There's our chlorine projected down. And here is yet another example where you can see that these two bulkier groups are in axial positions. They'd much prefer the equatorial position. And we label it as such. Okay, so what I would do is I'd go to the homework. I would start practicing doing these kind of three-dimensional sawhorse-ish chair conformers. One thing which I'm not going to talk much about, which I think is probably going to be in your book, Let me grab my model of cyclohexane, assuming my son gave it back to me. There are other conformers of cyclohexane that sometimes textbooks will talk about, but honestly, I don't think it's that useful. I just wanted to show you what they look like here. Maybe we'll get this out of here. Sorry, Steve. So, as you look at this thing, right, there's our chair. There is a type of conformation, which is a really high energy conformation, as you might expect, called boat, right? So it kind of looks like a little boat here. That's got a whole bunch of steric interaction. There's the thwacka. So that is really just kind of a form that exists only in the minds of chemists. Turns out the real thing that this thing is going to do what's called a twist boat. So these things keep bumping into each other. So what does it do? Well, it can either twist this way or twist that way. And of course, in my organic class that I took when I was a little tyke, we had to draw all these, and it was just like really worthless to me. It was something that really didn't provide much explanatory power, so I just kind of don't bother with it anymore. There's other forms, like for instance, like if you really want this thing to be flat, you can feel in the model kit how unhappy this thing is. Like if you feel in a model kit like a lot of like kind of springiness, like it's really not happy to be there, that is quite literally a high potential energy state that this molecule will do anything to avoid, right? So like I just have to hit it a little bit and it twists a little better with new model kits. So be aware of that. They do have like silly things like there's envelope, right? Where it kind of looks like an envelope where 5 of the carbons are held in the line. So don't be surprised if you read about that stuff. I think the most important thing is to be able to you do your chair conformers. In the next video, we'll kind of show how we can take these model kits and turn them into pretty useful flat structures as well. Take care.